I can use the principle of the law of conservation of momentum to predict the motion of one or more objects in a collision. So in this learning objective, we are using the principle of the law of conservation of momentum to predict the motion of one or more objects in a collision. So essentially, we're going to figure out what the total momentum of a system before is, and then since we know that the total momentum before must equal the total momentum after, we can use that information to then find what is the momentum of one of the objects in a system, and then more specifically, what is its velocity. Let's take a look at an example with a collision that is perfectly elastic. First off, we need to understand what a perfectly elastic collision is. We can essentially think of a perfectly elastic collision as the perfect bounce. If you dropped the perfect bouncy ball, it would hit the ground and come back up to exactly where you left it. That is the perfect bounce. Think of billiard balls. These technically are not perfectly elastic, and no collision in the world or in the universe is perfectly elastic, but they are pretty close to perfectly elastic. For this example, we have two objects. One object is moving to the right. It's a 2 kilogram object, and it's moving to the right with 2 meters per second. And we have one object that is stationary, so it is at rest. Its velocity is 0, but it is 5 kilograms. So we have a lighter object moving and hitting a heavier object. For all these problems, you should start with this expression right here. The sum of momentum before equals the sum of momentum later. After writing this expression, what you should do is then break this sigma up into what the individual momentum are. So like momentum 1 plus momentum 2. And let's go ahead and do that. And you might notice that I have color-coded the system to the right. Green is going to be the left object, and blue is going to be the right object. When we break the sigma into the sum of all of the individual momenta, we're going to start with the momentum of the object on the left. So that is green momentum initial. And then we're going to add to that the momentum of the object to the right. So the momentum initial of the blue object. And we're going to set that equal to their later momentum. So the momentum final of the green object and plus the momentum final of the blue object. Now that we've broken the sigma into each individual object, what we should do is now we're going to unpack the momentum into mass times velocity. So the initial momentum of the first object, we're going to have the mass of that object times the initial velocity of that object. And then we're going to add to that the mass of the blue object times the initial velocity of the blue object. We're going to set that equal to the mass of the green object times the velocity at a later point in time of the green object, plus the mass of the blue object times the velocity at a later point in time of the blue object. At this point, what we should do, before plugging in any variables or any values, we should identify any zero values right away. Zero values are really handy to plug in right when you notice them, because that's going to simplify the expression down. You can see from the example, the blue object is initially at rest. It is not moving. That means its velocity is 0. So if we look at this term, the initial velocity of the blue object is 0. That makes the entire term, the entire initial momentum of the blue object 0. That will simplify our expression down to the mass of the green object times its velocity equaling the mass of the green object times its final velocity plus the mass of the velocity of the final object, the mass of the velocity of the blue object. What we're solving for is the final velocity of the blue object. So what we're going to do now is we're going to solve this expression for the final velocity of the blue object. To do that, we're going to subtract from both sides the mass times the final velocity of the green object. And then we're going to divide both sides by the mass of the blue object. This gives us a final expression of the final velocity of the blue object is going to equal the difference in the momentum before minus after of the green object divided by the mass of the blue object. Let's plug in some values now. We need to be careful at this point. I was just about to put in the velocity, the final velocity for the green object. The green object originally has a velocity going to the right at 2 meters per second. At a later point in time, it has a velocity going to the left at 1 meter per second. Now notice in this diagram, it did not include negative or positive, but we know that we're going to have to assign one direction positive and one direction negative. Since I already plugged in a positive value for the initial velocity of the object, we're going to set going to the right as positive. That means going to the left must be negative. So when we plug in, and this is one of the most common mistakes students make, when we plug in the velocity after for the green object, we need to make sure to plug in a negative 1 meter per second. And since we were already subtracting it, that's actually going to wind up making this a addition symbol instead. So on the top, we get 6 kilograms times meter per second, and on the bottom, we get 5 kilograms. Now notice the kilograms on top and bottom are going to cancel, and this is going to leave us with just meters per second, which makes sense because what we're solving for is a velocity, so we should get meters per second. And our final answer is 1.2 meters per second. Let's take a look at a case where we have a perfectly inelastic collision. Now, an inelastic collision is essentially the opposite of an elastic collision. For an elastic collision, we thought of as a perfect bounce. This would be no bounce. If you dropped an object and it did not bounce back up at all, that would be an example of a perfectly inelastic collision. For this example, we're going to have the exact same scenario, but this time, instead of bouncing off of each other, they're going to stick together. That's another characteristic of a perfectly inelastic collision. Objects will stick together in a perfectly inelastic collision. One example I like to use for students is a car crash. In a car crash, often the cars don't bounce off each other. They stick together because they mold and shape and get deformed around each other. To approach this problem, we're going to start the exact same way we start with all problems using conservation of momentum. We're going to start by writing this expression. The sum of a momentum before equals the sum of momentum at a later point in time. Breaking that sigma up, we're going to have the momentum initial of the green object plus the momentum initial of the blue object. And that's going to equal the momentum of the final of the green object plus the momentum final of the blue object. Right away, we can recognize that the momentum initial of the blue object is just going to be 0. So again, let's simplify this down. We get the momentum initial of the green object is going to equal the sum of momentum. Let's use the equation for momentum to break momentum into mass and velocity. The key to solving a perfectly inelastic collision problem is to recognize that in the end, they're going to be stuck together. When two objects are stuck together and they stay stuck together, they're going to be moving at the same speed. Because if these two objects were not moving at the same speed, one would be going to the right, maybe faster than the other one. Their distance between each other would grow larger. Right now, they're stuck together. So you can think of this as essentially one object. The velocity final of the blue object is actually going to equal the velocity final of the green object, which for this sake, we're just going to call velocity. So let's go ahead and substitute in velocity for velocity final of green and the velocity for velocity final of blue. What you should notice is that we have two terms that both have the same variable. Two terms with the same variable. We could write this another way. We can factor out that velocity. So we take it out of both terms and put a parentheses and then put what's left over, which is m of the green object plus the mass of the blue object. Let's remind ourselves that what we're solving for is the final velocity of both the objects, or just the final velocity. So let's go ahead and solve this expression for just the final velocity. Now let's plug in some values and make sure that we correctly apply negatives and positives. However, it looks like everything is either going nowhere at all, so it's either has a velocity of 0, or it has a velocity going to the right. So we shouldn't have to deal with any negatives here. Once again, we're going to have all the kilograms cancel because the top of this expression, the top of this fraction, has only one term and it has kilogram in it. And the denominator of this fraction has two terms, but both have kilogram in them. If both terms in the bottom of the fraction did not have kilograms in it, we would not be able to cancel them like we're doing now. because essentially what we're doing is factoring out the kilograms. So then we have kilograms being multiplied by everything on the bottom. So then we can cancel it. So in the end, we get that the final velocity of the entire system, so the final velocity of these two objects when stuck together, is going to be equal to 0.571 meters per second, positive, so it's going to the right. I just want to point out, when I said before that you could treat these objects as, or these two objects when stuck together as one object, we can see how that works out in the expression. If we go back up to this line right here in the expression, where we factored out the velocity, essentially what we have is, we have these two masses added together. We could just call that a new mass. Let's call it mass total for the total mass. And then we're multiplying it by the velocity. And then look at that expression right there. That expression right there is a mass times a velocity, so that's momentum. It's momentum total. So essentially we can just treat the two objects when stuck together as if they were just one object with a combined mass of both objects. Let's take a look at a third example. This one's going to be the most tedious because no velocity is going to be zero. For each of these problems, we start with the expression. Sum of all momentum initial equals the sum of all momentum final. For this example, we have two objects. The object on the left is going to the right at 5 meters per second, and it's a 2 kilogram object. The object to the right is going to the left, and it's a 3 kilogram object going 2 meters per second. Whenever we approach one of these problems, we need to specify what is the positive direction and what is the negative direction. So the positive direction is going to be to the right in this case. After writing the sum of all momentum initial equals the sum of all momentum final, you should then break the sigma up into each individual object. So we have the pink object and the green object, and we have their initial momentum. And then we set that equal to the momentum final of the pink object and the momentum final of the green object. After expanding the initial expression into each object, the next task is to expand the momentum into the variables that make up the momentum, using the expression momentum is equal to mass times velocity. The mass doesn't change of these objects, but the velocity does. So we have an initial velocity, and later we have a final velocity on the right side. So we rewrite momentum as mass times velocity for all of the terms. Let's recognize what we're solving for. We are solving for the final velocity of the green object because it's the only value that we do not have. And if you're only missing one value in an expression, in an equation, then you could solve that equation. The next step would be to subtract the final momentum of the pink object from both sides to move it over to the left side, and then divide both sides by the mass of the green object. This solves for the final velocity of the green object by itself. So the final velocity of the green object is going to equal the mass times the pink object's initial velocity minus the pink object's final velocity. What we did was we took this expression here, the mass times the velocity initial of pink minus mass times velocity final of pink, and we notice that the two masses here are the same mass, so we can factor that out from the expression. So we can get a mass times the quantity of these two velocities subtracted to each other. And then we're going to add the mass of the initial momentum of the green object, which is mass times the velocity initial, and divide by the mass of the green object. One thing I want to point out right here, a very, very common mistake might be that students always want to cancel this mass right here and this mass, but you cannot do that. It is probably the most common algebra mistake I see every year. You cannot cancel a variable that only appears in one out of multiple terms. If there was only one term on the top, then every single term on the top would have this mass, this green mass, and every single term on the bottom would have this green mass, so then you could cancel them out. But not every single term in the top expression has the green mass, so you cannot cancel it out. Because what we're doing by canceling it out is we're saying that we can factor it out from the whole expression. But we can't factor it out from the whole expression because not every single term has the green mass in it. Then we plug in our values. One thing to note, the final velocity for the pink object is negative because it's going into the negative direction. Once again, we get that the kilograms cancel because every single term has a factor of a kilogram on both on top and bottom. So they can cancel out and we get meters per second as our units, which is what we expect because we're solving for a velocity. In the end, we get 16/3 meters per second. One important thing to notice here is that there was no guarantee in this problem that the final velocity was going to be positive. Also, we should notice, what does a final velocity of positive mean? Positive velocity means that this object in the end is going to the right. It started by going to the left, but it ends by going to the right. And we know it's going to the right because we have a positive value for the velocity. If we ever had a negative velocity, it would be going to the left. Here are two practice problems. The first practice problem, you have a 25-gram bullet entering a 2.35 kilogram watermelon and embeds itself into the melon. This keyword here, embeds itself, essentially means that this bullet is going to stick into the watermelon and make them essentially one object with a combined mass. So this is a perfectly inelastic collision. The melon is set immediately into motion with a speed of 3.82 meters per second. The bullet remains lodged inside the melon. What is the entry speed of the bullet? So here, unlike the previous examples I showed you, we are solving for the initial velocity of the bullet. That's fine. As long as we can write the expression, we can just solve for some other variable. One key note here, though, we need to be careful of the units of mass because the bullet is in grams, but the watermelon is in kilograms. Have to have the same unit of mass. The second practice problem, we have a 3,000 kilogram truck moving to the right with a speed of 5 kilometers per hour, and it collides head-on with a 1,000 kilogram car moving to the left with a speed of 10 kilometers per hour. The two vehicles stick together and move with the same velocity after the collision. So again, perfectly inelastic collision. Determine the post-collision velocity of the car and the truck. Now be careful of the plus and minus sign on the velocity of the two vehicles. For both these problems, I have given the final answer, but you have to do the work.